The first of these books, the first 3 minutes, was written at a time when I hadn't really thought about writing about science for general readers. I was very much involved with research on elementary particle theory. But I had recently come to join the Harvard faculty, and I was asked to participate in the opening of a new building on the Harvard campus, a Center for Education of Undergraduates in Science. And I was asked to talk about some topic in science. And I wanted to talk about something that would be exciting to a lot of people and not too mathematical. And I had been very excited by the opening up of our understanding of the early universe that started with the discovery of a microwave radiation filling the universe, discovered in 1964. And so I thought I would talk about what we had learned from that about the early universe. And when I say the early universe, I'm referring to the fact that the universe is expanding and cooling. So there was a time in the history of the universe when matter was much more dense and hot. So dense and hot, in fact, that ordinary atoms and even the nuclei of atoms could not hold together. And you just had, certainly not stars or galaxies, the universe was filled with a soup, more or less homogeneous, of elementary particles: protons, neutrons, electrons, neutrinos, photons. And we can calculate what happened in the first few minutes of the expansion of the universe as this soup expanded and cooled until at the end of approximately the first 3 minutes, it became cool enough for the nuclei of atoms. Nuclei like deuterium, the nucleus of heavy hydrogen, and helium. It became cool enough for them to hang together and not be blasted apart by the radiation. So I planned a talk in which I went through something like a cinema of the expansion of the universe, describing how the universe expanded and cooled, and neutrons decayed into protons, and then at the end of 3 minutes, helium nuclei began to be formed, and we had something approaching the universe we know about now, filled with hydrogen and helium. And, well, I gave a talk along those lines, and I thought that would be the end of it. But a friend of mine who, not a scientist, but, well, not a physicist, but a sociologist, Daniel Bell, heard the talk and was excited by it. Who would not be excited by knowing what was happening? I think this is what he really was excited by, not the specifics, but the fact that science had progressed to the point where we could really talk seriously and with some confidence about what was happening in the first few minutes of the expansion of the universe. And he told a publisher, Erwin Glickus, the publisher of basic books about it. Glickus got in touch with me and suggested I write a book along these lines. I thought it was not, well, I found myself attracted by the idea of being able to reach out to people who were not my colleagues in physics, but educated people of all professions who might be interested in the history of the universe. So I did write the book, and it was successful. It won some prizes, and it was translated into 22 foreign languages, some of which I had never heard of. That was my first book on science for general readers. Am I taking too long with this? Is this all right?
Go on, please, go on.
I'll continue with the second book. Over the years, not only when writing for the general public, but also in writing serious mathematically complex treatises on general relativity and quantum mechanics and quantum field theory, I've always found it helpful to include a historical introduction. I've gotten more and more interested in the history of science, partly because I like to feel that the work we are doing today in science is part of a great historical tradition going back to, especially to ancient Greece. And the little histories I was writing and the books I have written in the past were mostly about modern scientific history, and I wanted to learn more about the history of science in the past, not because, of course, they didn't know what we know now, but because I felt that their standards of judging truth and their aims in seeking truth were different from ours, and I wanted to understand in what way the science of the past was fundamentally different from now, not just in its content, but in its aims and standards. And so I did whatever I do when I want to learn something, which is I teach it. I volunteered to teach courses in the history of science, some to graduate students, some to undergraduates here at the University of Texas. And as often happens when I teach a subject, I find my lecture notes, after several iterations, turn into a book. And that happened. I wrote a book on the history of science, in particular the history of physical science, physics and astronomy. I don't know that much about the history of biology. Going back as far as I could go back to the pre-Socratics, the Thales, then carrying the story forward to Plato and Aristotle, and then to what I regard as the great flowering of science in the ancient world in Alexandria, in the period from the death of Alexander through the period when Alexandria became part of the Roman Empire, and until the adoption of Christianity and the decline of the Roman Empire in the West, when science really largely disappeared in Christendom, although it was continued and flourished for a while in the lands of Islam. And then picking up the story with the rebirth of science in Europe in what is called the scientific revolution, starting with Copernicus and working up to a climax with the work of Isaac Newton. And I emphasized what so interested me and impressed me, that these scientists of the past not only had to learn what we now know about matter and about the solar system and so on, but they had to learn how to learn. That the standards, for example, Aristotle would always ask, what is the purpose of something like fire or the earth? That's a bad question. Things like inanimate objects don't have purposes. Is there any purpose in the universe? I don't know, but there's certainly no purpose in the solar system. It's wrong to ask, as Aristotle would, what is the natural condition of things. What is the natural place, for instance, of Earth? He thought the natural place of Earth is at the center of the cosmos. We not only don't agree with that, we don't think it's the right kind of question to ask. And this, for me, has been the most interesting aspect, which I wrote about in this book. The gradual learning how to learn. So I'm prepared to answer any questions you might have.
Okay, thank you very much for your comments. Θα ρωτήσω στα ελληνικά στο ακροατήριο αν έχει κάποιος να ρωτήσει κάποια ερώτηση ή ζητήσει κάποιο ιδιαίτερο σχόλιο από τον καθηγητή Weinberg και αυτό μεταφέρω προς τα ελληνικά. Παρακαλώ.
Μπορείτε να ρωτήσετε τον κύριο Weinberg πόσο επηρέασε τη σκέψη του Κοπέρνικου ο Αριστοτέλης, εφόσον η άποψή του ήταν ότι το σύστημα του είναι γεωκεντρικό, όχι ηλιοκεντρικό.
Τον Αριστοτέλη τον Αρίσταρχο.
Ο Αριστοτέλης υποστήριξε ότι το σύστημα είναι γεωκεντρικό. Ενώ ο Κοπέρνικος απέδειξε ότι το σύστημα είναι ηλιοκεντρικό. Σε τι επηρέασε ο Αριστοτέλης τη σκέψη του Κοπέρνικου, θετικά ή αρνητικά?
Professor Weinberg, one of the people here asks your opinion on the way Aristotle influenced Copernicus in his trial to construct the heliocentric system.
Aristotle had his own theory of the solar system in which the planets are bright spots on spheres that revolve around the Earth. And the spheres are connected to each other in a complicated way to account for the fact that sometimes planets seem in their movement through the zodiac to turn backwards. This is particularly visible in the planet Mars. Aristotle's scheme had been largely abandoned by the time that Copernicus started to work. It doesn't agree with observation. The real contrast for the work of Copernicus is with the work of Claudius Ptolemy, some 350, I'm not sure, hundreds of years after the death of Aristotle. He worked in Alexandria, but during the period when that had become part of the Roman Empire. And Ptolemy had a different scheme in which the Earth is at rest, the sun goes around the Earth, and the planets go around the Earth, but not with the Earth as the center of their orbits. The centers of they go around on circles called epicycles, and the centers of those circles go around the Earth. The Ptolemaic scheme was very clever and did agree with observation to a high accuracy, not perfectly, but quite well. And Copernicus used it as a source of data for his work. He did not rely on his own observations. He relied on the observations that were crystallized in the system of Ptolemy. And all he could show is not that his theory fit observation better than Ptolemy, but that it was simpler and that because the complications in Ptolemy's theory arose from the fact that in fact it's the Earth that goes around the sun, he could account for those complications in a much neater and more natural way. The competition for Copernicus was not Aristotle, at least as far as professional astronomers were concerned, but Ptolemy. And in fact, when Galileo wrote his famous dialogue concerning the two chief systems of the world, the two chief systems of the world that he was considering was not Copernicus and Aristotle, but Copernicus and Ptolemy.
Thank you very much. Let me... Excuse me?
Υπάρχει στοιχειώδες σωμάτιο? Ρώτησε.
Just like that.
Αν υπάρχει στοιχειώδες σωμάτιο.
Now we have a question, Professor Weinberg, which seems to be a bit philosophical. Are there elementary particles? One elementary, you mean one?
One, two, but not 18.
Are there one or two or a little elementary particles? For sure, not a lot. As it is known, the elementary particles, according to the standard model, are nearly 60 or something like that, if we count all the expressions they have. Do you think that there is another level of physics beyond that, where the elementary particles are not 60 or 20 or 80, but maybe one?
One, two.
Well, our present theories are certainly complicated enough so that we have a very strong feeling that our present theory is just an approximation to a deeper theory, which has to be more simple. I don't think there are 60 or 80 elementary particles in our present theory, but it depends on how you count them. There are quarks and leptons and gluons and W, Z, and photon and Higgs boson. But however you count them, there are too many. I agree with you about that. But the final theory, which we hope we'll learn someday and which we hope will be much simpler, and will have our present theory, the so-called standard model, as a good approximation, that final theory may not be a theory at all. I very much doubt that it's just going to be a theory of one type of particle or a few types of particle. It may be a theory that doesn't refer to particles at all, like, well, it could be a quantum field theory with just a few kinds of fields, but they would be fields that form a few families of fields, let's say. All of the particles would be little bundles of energy and momentum of those fields. For example, we have a field theory of the strong nuclear forces where the forces are carried by particles called gluons. Well, there are actually 8 types of gluons, but they form a tightly knit family. And we know why there are 8, and they're all closely related to each other. There is an argument based on group theory that it has to be 8. And that isn't the kind of complication that bothers us. So there may be similar families of particles that are all quanta of a very limited number of field types. Or it may be something quite different. It may be something like a string theory. And in fact, the physicists who pioneered the development of string theory think that there is just one fundamental entity, which is a string. Think of it as a little loop that's vibrating. It has different modes of vibration, which we see as different kinds of particle, but it's still just one basic kind of string. With its own tension that causes the vibration. That may be true. We don't know what the final theory is. I certainly would not expect that it's a theory like our present theory, but with just fewer elementary particles. That seems unlikely.
Thank you. Any other question?
Ναι. Αν μπορείτε να ρωτήσετε τον κύριο καθηγητή, ποια είναι η σωστή προσέγγιση για τη γνώση κατά αυτόν και πώς αυτό επηρέασε τη δική του έρευνα.
Ποια είναι η σωστή προσέγγιση για τη γνώση?
Ναι, επειδή είπε ότι τον ενδιαφέρει πάντα στην ιστορία, πώς οι φυσικοί παλαιότερα, ας πούμε, έπρεπε να μάθουν τον εαυτό τους να κάνουν σωστές ερωτήσεις.
Ναι.
Και τελικά, ουσιαστικά, ποιες πιστεύω ότι είναι οι σωστές ερωτήσεις για να ρωτήσει ένας φυσικός ώστε να καταλήξει στη γνώση εν τέλει, στην αλήθεια, ουσιαστικά.
Well, I have a difficult question, which is not mine actually. It comes from one of my students. What are the correct questions for a physicist in order to find the right answers? Is that correct or not?
What are the correct questions in order to find the right answers? Well, that's, you know, that the whole history of science has been a history of the discovery of what are the right questions to ask. In the context of trying to go beyond our present theory, the Standard Model, but not too far beyond it, imagining a theory which is not very different, we would ask questions like, what is the symmetry group that unites all the forces of the Standard Model? Or what family of particles has all the known particles, or perhaps I should say, what family of fields has all the known fields of the Standard Model as just special cases? Can we make a beautiful theory with just one family of particles all tied together by some grand group of symmetries? Those might be the right questions. It may be that the next big step in physics will come from answering those questions. But it might not be. It might be that the next big step will involve a completely different kind of theory, not a field theory at all. And the example that I have in mind is string theory, but maybe that's not the right kind of theory at all. In the end, we know the question. The question is, what are the laws of nature? You know, that's such a big question that it doesn't help you very much to go around repeating what are the laws of nature, what are the laws of nature. And what is the right question to ask in our present state to get us to the next step? I don't really know. We can guess. But that's something we have to learn.
Thank you.
Θα ήθελα να ρωτήσω, εάν βρίσκει ο καθηγητής ότι η σκέψη, η μέθοδος των αρχαίων Ελλήνων των προσπερικών παραδείγματος χάρη προς εκτέλει και στον πρώτο περίπτωμα, εάν μοιάζει, και αν μοιάζει σε τι διαφέρει από τη σημερινή επιστημονική σκέψη.
Well, the question now has to do with the past. What do you think on the relation between the scientific method or the method, let's say just the method, of the pre-Socratics, the philosophers, the ancient philosophers? What's the relation of this method, the way they used to, you know, to deal with the problems of physics, with the scientific method of today? Do you think that there is a strong relation or a strong connection, or they are very different? How they are related?
Well, I'm not sure I understand the question. Am I correct that you're asking what is the relation between the scientific method used in the ancient world and today?
Yes.
Exactly.
Pre-Socratic.
Yeah, well, I would have to change the question a little because there was great change in the ancient world. For Plato and his predecessors, the scientific method was really closer to poetry than to what we would call science today. It consisted of making up hypotheses about the nature of matter or the nature of the solar system, and just stating them in as eloquent a way as possible. So Democritus, in language which is very poetic, says everything is atoms. And Thales, well, we don't have anything written by him, says everything is water. And then Plato says everything is atoms, and the atoms are atoms of water, earth, fire, and air, and I will tell you what those atoms look like. It's all poetic guesswork, and without any attempt to verify. Democritus, in all his writings, never explains why you should believe that all matter consists of atoms. Plato, at one point, he says, I could try to explain why the shapes of the atoms are what I say they are, but it would take too long, and maybe I'll come back to it later. He never does, of course. The scientific method starts to change with Aristotle, who for the first time seems to have understood the necessity of confirming his theories by observation. But Aristotle does not use mathematics. For instance, he very cleverly not only guesses that the Earth is a sphere, but presents arguments why you should believe that the Earth is a sphere. For instance, the appearance of the night sky changes as you move north and south, or south, as a traveler goes north or south. A very clever and correct argument, but he never uses mathematics to infer from that how large the Earth is. That is done in the Hellenistic era, largely in Alexandria, by scientists using mathematics and observation together. Scientists like Eratosthenes, Aristarchus, Hieron, and of course Archimedes and Ptolemy, who I think have pretty much the same scientific method as we have today. Make observations, use mathematics to formulate theories, and then check those theories against further observations. But with some confusion still about the relation of mathematics to science. Hero, for example, in proving a theorem that says that when light strikes a mirror, it's reflected off at the same angle with which it hit the mirror. He proves that theorem using a hypothesis that light will always travel on the shortest possible path from the source to the mirror to the eye, or actually he thought it went the other way, from the eye to the mirror to the source, without feeling the necessity of explaining why that fundamental principle is true. And that confusion about the relation between mathematics and science continues. In fact, Isaac Newton was not a professor of science or astronomy or physics. He was a professor of mathematics, as if you could learn about the solar system just by doing mathematics. I think the first person who clearly stated the modern scientific method, including the correct account of the relation of mathematics and science, was the Dutch physicist Christian Huygens. And in my book, there's a quote of a paragraph of Huygens, which is quite remarkably modern in its tone. And yet, it needed, this was written in the 17th century, late 17th century, and it's really striking that it took that long before people began to understand correctly how observation and mathematical theory go together to make a physical theory.
Thank you. Any other question?
Έχοντας σαν ξεχωριστό μέρος της ερευνητικής του δουλειάς την ενοποίηση πεδίων, της ηλεκτρομαγνητικής δύναμης και της ασθενούς αλληλεπιδράσεως, πόσο αισιόδοξος είναι ότι κάποια μέρα θα καταφέρουμε να ενοποιήσουμε όλες τις δυνάμεις κάτω από μία θεωρία?
Starting from the fact that you were one of the pioneers for the unification of forces, what are your thoughts on the possibility to unify all four interactions in the near future?
Well, I think everything has to be unified in the end. We're looking for a simple theory without a lot of different types of force or particle or whatever. But you said in the near future, and I'm afraid I'm rather pessimistic these days, rather sad, because the Standard Model, which simplified a great deal that had appeared so confusing in the 1950s and 1960s, the Standard Model was pretty well complete in its modern form by the end of the 1970s. It has then been repeatedly verified with the discovery of neutral currents, and then the discovery of the W and Z, and then the discovery of the Higgs boson, discovery of new types of quark. But we have nothing new that goes beyond the Standard Model. We have hints. The astronomers tell us that 5/6 of the mass of the universe, the material particles, the mass of the material particles of the universe is not in the particles of the Standard Model, but is some kind of dark matter. And we don't know what that is. There's also dark energy, which is an energy not in any kind of particle, but in space itself. We don't know what that is. And there's also the problem of incorporating gravitation. We don't quite know how to do that. But what I just said are outstanding problems. We've been facing those problems for decades, certainly more than 2, and in some cases much more than 2 decades, and we're not making any progress. There's also now very small neutrino masses, which require something beyond the minimum Standard Model. And we have an idea what that is, but it's a very vague idea. And we're not making progress. It's a long time since I've heard of any experimental result in elementary particle physics that requires a change in our existing theory. And that is sad. I hope in the near term, the best hope I think is to discover a violation of some conservation laws that keep ordinary matter stable, that, for example, prevent the nucleus of hydrogen, the proton, from having a radioactive decay. I think it's very likely that protons do decay radioactively with a half-life that's too long for us to have observed it, but might not be too much longer than about 10 to the 30 years, for example, but might not be so long that by watching tanks of water, for example, deep underground for years, we might not occasionally see a proton decay. Well, that would probably be the most exciting thing I could imagine that might set us on a path toward a really new theory which solves some of the problems, maybe not all of the problems of the standard model. And those observations are continuing. But when they're going to see proton decay, who knows? I don't know. I'm hoping something will happen while I'm still here to learn about it. But I'm not confident of that.
Thank you very much. Professor Tsangas wants to ask a question.
Professor, you mentioned just before dark matter and dark energy. And I would like to ask you, what is your feeling about this recent accelerated expansion of the universe and the approaches that have been suggested to explain it? What is your opinion and your gut feeling?
Well, there's nothing new to say about dark matter except that there have been extensive searches for it, both searches for its decay products, for the products of the collision of dark matter particles in which they annihilate ordinary particles. There's been a search for that. It hasn't discovered anything. There's also a search for dark matter particles hitting or experimental detectors which can register that a dark matter particle is hit. Those are very difficult because whatever you do, you're always being hit by cosmic rays or by neutrons from radioactive decay across to the Earth. And so far, nothing has been seen that is unambiguously a dark matter particle. And there's also a hope that dark matter particles might be created at CERN in collisions of ordinary particles. And so far, nothing like that has happened. We don't know. Maybe dark matter will be discovered soon, but there's no reason to hope it will. There's no reason to expect it will. We certainly can hope it will. As far as dark energy is concerned, the only way we know about it is through studies of the expansion of the universe. It's the only thing it affects, causes, as you said, the expansion of the universe to speed up. We can study the way it's speeding up. The simplest hypothesis is that the dark energy is just a constant energy per volume. So many calories per liter of space. And obviously a very small number. It's just a constant. And so far, all observations are consistent with it just being a constant. That is sad, because if it was varying, the rate that varies would give us a clue as to what it is. And there are observations going on right now, including a program at the McDonald Observatory in West Texas, which is run by the University of Texas, where I work, that is trying to measure the history of the expansion of the universe, going back in time in a way that would give you information about whether the dark energy is changing with time. These observations have not yet gotten to the point where they're able to answer that question, and so far, no one has. Again, I hope that some astronomical group will discover change in the dark energy which will allow us to begin to study it by the ordinary methods of astronomy. My best guess, you know, if you want to just ask if I had to guess, what would I guess? I would guess that the dark energy is a constant. It is a constant which is determined by the laws of physics involving other constants that we don't know, so that we're not able to calculate it. And it may be that it is not a universal constant, but that this is a very controversial idea, but studied by many people these days, that we live in a kind of multiverse where the universe, there isn't just one Big Bang, but there are many Big Bangs. In each of them, the laws of nature and the constants of nature are different, and the value of the dark energy may vary from one to the other. And in most of them, it's quite large. It's large like the kind of density of energy you expect in elementary particle physics. And in those Big Bangs, there's no one to ask the question, because those Big Bangs expand so rapidly, there's no time. Not only is there no time for life to evolve, there's not even any time for stars or galaxies to appear. And then every once in a while, here and there, there is a Big Bang in which the dark energy, just by accident, happens to be small enough to allow time for life to evolve. And we, of course, live in one of those rare Big Bangs. It's like on most planets, are not suitable for the appearance of life. It's too hot, or it's too cold, or it's all gas, there's no solid surface, or there's no water. And every once in a while, perhaps one solar system in each galaxy, something like that, the conditions are just right so that life can appear and evolve. And it is only on those planets where people are asking the question, why is the Earth such a comfortable place on which to live? The answer would be, it's a comfortable place because if it wasn't, you wouldn't be asking the question. And in the same way, why is the dark energy so small compared to what you expect in elementary particle physics? It may be the answer is because if it wasn't, you wouldn't be asking the question.
Thank you very much, and let's thank Professor Weinberg.